Federated learning systems are vulnerable to model poisoning attacks due to their distributed nature, making it challenging to detect and defend against backdoor attacks. To address this issue, a novel approach, CosDefense, is proposed, utilizing a cosine-similarity-based attacker detection algorithm to secure federated learning against model poisoning attacks via client filtering. CosDefense operates by calculating the cosine similarity score of the last layer's weight between the global model and each client update. Clients with scores significantly higher than the average are labeled as malicious and filtered out of the model aggregation in each round. This approach does not require any additional information beyond the received model updates and is compatible with client sampling. In contrast to existing defense schemes, CosDefense has several merits. It does not require representative benign data, and it only accesses the global model parameters and client updates, eliminating the need for extra information. Existing schemes often rely on critical drawbacks or unfeasible assumptions, such as requiring representative benign data at the server or diminishing the aggregation coefficients of likely malicious clients. Notably, the weight inside the last layer of the local model update is more sensitive to the local data distribution than other layers. This sensitivity enables the detection of poisoning updates before model aggregation, allowing for effective filtering of malicious clients. Experimental results on 3 real-world datasets demonstrate the robust performance of CosDefense under state-of-the-art Florida poisoning attacks. These findings highlight the efficacy of CosDefense in securing federated learning systems against model poisoning attacks. In federated learning settings, existing backdoor defense methods exhibit limitations, prompting the development of CosDefense, a novel approach for detecting and filtering malicious model updates. A comparative analysis with other Florida backdoor defense methods, as shown in Table 1, highlights CosDefense's unique advantages, including compatibility with client sampling, validation data at the server, and no requirement for information about the number of malicious clients per communication round. The authors investigate layer-wise cosine similarity for model weights, focusing on how backdoor attacks are reflected on the server side during Florida training. They observe that the last layer's weight is more sensitive to the input data distribution and quantify model weight similarity using cosine similarity. An experiment involving 10 clients training a 4-layer CNN-based model on the Noniad partitioned MNIST dataset reveals that input-side layers exhibit higher similarity than output-side layers, with the last layer displaying the lowest similarity score. This indicates that local data label distributions are efficiently reflected in the last layer's weight compared to other layers. Building upon these observations, the authors propose CosDefense, which filters malicious model updates on the server by calculating the cosine similarity between each collected model update and the last global model. This method identifies and eliminates outliers, preventing backdoor attacks in Florida settings. By leveraging the distinct characteristics of the last layer's weight, CosDefense provides a more flexible and robust solution compared to existing methods, enhancing the security of Florida against backdoor attacks. The proposed research introduces a novel method for detecting malicious clients in federated learning, a critical challenge due to the distributed nature of the learning process. By focusing on the cosine similarity between the global model weights and local model updates, the authors identify potential threats. In a benign scenario, the cosine similarity tends to decrease as training progresses, indicating that the direction of benign updates is less than perpendicular to the global model, contributing to its convergence. However, in the presence of malicious clients, the cosine similarity increases, suggesting that these updates align with the global model parameters and hinder its convergence. To demonstrate this concept, the authors trace the average cosine similarity score of the last layer's weight between all received local updates and the global model under both benign and poisoning attack cases. They observe that the average cosine similarity increases sharply after launching an IPM attack, confirming their speculation. This increase indicates that cosine similarity scores from malicious clients are much larger than those from benign clients, preventing the convergence of the global model. The authors then propose CosDefense, a server-side clustering-based defense method. This method calculates the cosine similarity between the last layer's global weights and the last layer's local updates for each client in each round. Clients are clustered based on their cosine similarity scores, with those having much higher scores labeled as malicious and excluded from aggregation. This approach is compatible with any aggregation method and allows the server to perform aggregation with only benign client updates. The evaluation setup involves conducting experiments on 3 datasets MNIST, FashionMNIST, and CIFAR10 using a 4-layer CNN-based model and ResNet-18 model. The Noniad partition for all datasets is generated following previous Florida works, with a default Q value of 0.5 representing a higher Noniad degree. The authors compare their method with previous related works, highlighting the significance of detecting malicious clients in federated learning environments. In federated learning, the authors assess the efficacy of CosDefense, a novel defense method, against state-of-the-art model poisoning attacks. CosDefense is compared to 2 robust aggregation rules, crumb and clipping median, on 3 datasets, MNIST, FashionMNIST, and CIFAR10. The inner product manipulation, IPM, attack is employed to simulate real-world adversarial scenarios. Experimental results reveal that CosDefense surpasses crumb and clipping median in terms of accuracy, recovery speed, and time after the IPM attack commences. Notably, CosDefense performs exceptionally well on the most challenging dataset, CIFAR10. The authors further investigate the impact of varying the number of attackers, from 10% to 40% of total participants, on the Noniad partitioned MNIST dataset. The findings demonstrate CosDefense's robustness and reliability under both small-scale and large-scale attack scenarios, achieving the highest accuracy compared to other baselines across all attacker ratios. This research contributes significantly to enhancing the security of federated learning against malicious model updates, providing a more reliable and efficient defense mechanism against model poisoning attacks. In the concluding section of their research paper, the authors present CosDefense, a novel cluster-based defense scheme designed to filter out malicious updates in model aggregation on the server in federated learning settings. The experimental results demonstrate CosDefense's robust performance against state-of-the-art Florida poisoning attacks, highlighting its potential as a reliable defense mechanism in this field. The authors acknowledge the support received from various organizations, including the Defense Advanced Research Projects Agency, DARPA, ARROW, and ONR, under specific contract numbers. They clarify that the views expressed in the paper are those of the authors and do not represent the official views or policies of the Department of Defense or the U.S. government. The paper cites several sources, indicating a thorough examination of existing literature on the subject. This adds credibility to the findings and reinforces the significance of CosDefense as a groundbreaking contribution to the field of federated learning security. The authors' work underscores the importance of addressing vulnerabilities in model aggregation processes, particularly in light of increasing concerns about data privacy and security in distributed machine learning environments. By developing and testing CosDefense, they have provided a valuable tool for researchers and practitioners seeking to enhance the resilience of their systems against potential threats. Overall, the paper presents a comprehensive analysis of the challenges posed by malicious updates in federated learning and introduces a promising solution in the form of CosDefense. The findings and implications discussed throughout the paper are crucial for advancing our understanding of security measures in distributed machine learning systems and paving the way for future research in this area. This section of the research paper presents a comprehensive compilation of key terms, concepts, and methodologies employed in the study. It serves as a reference guide for researchers and stakeholders to ensure clarity and precision in understanding the technical aspects of the research. The paper begins by defining critical terms such as quantum entanglement, superposition, and quantum decoherence, which are fundamental concepts in quantum mechanics. These definitions provide a solid foundation for understanding the complex phenomena discussed throughout the paper. The section also delves into the methodologies used in the study, including quantum teleportation protocols and entanglement swapping techniques. These methodologies are crucial for the experimental setup and data collection processes, allowing researchers to accurately measure and analyze quantum states. In addition to defining key terms and methodologies, this section also summarizes essential mathematical concepts and algorithms. For instance, it explains the Schrödinger equation and its role in describing the time evolution of quantum systems. The Bell state measurement algorithm is also discussed, highlighting its importance in detecting entanglement between pairs of qubits. Furthermore, the paper includes a detailed description of the experimental setup, which involves the use of optical fibers and photon detectors. This setup enables researchers to test the efficiency of quantum communication protocols over long distances. The section concludes with a discussion on the limitations of the study, including potential sources of error and areas for future research. This provides valuable insights for researchers looking to build upon the findings presented in the paper. Overall, this comprehensive list serves as a valuable resource for those seeking to understand the technical nuances of the research. By providing clear definitions, detailed methodologies, and summaries of complex mathematical concepts, it ensures that readers can fully appreciate the significance of the study's findings. This paper, presented at the ICLR 2023 workshop on backdoor attacks and defenses in machine learning, delves into the federated learning setting with a focus on data poisoning attacks. It explores a distributed optimization problem where the aim is to minimize the global objective function f, theta, which represents a weighted sum of local objectives from k clients. Each client's local objective, f_i, theta, signifies the loss function of the client's local data distribution. The weights, p_i, represent the aggregation weight of each client, adhering to the conditions p_i is greater than or equal to 0 and sigma p_i equals 1. The federated learning algorithm follows a standard protocol. In each communication round T, the server selects a subset of clients, S_T, for client sampling and dispatches the current global model parameters theta_T to these selected clients. Each client then performs local model updates using their local data and transmits the model update, G_I T+1, back to the server. The server aggregates these updates using a function G_T and obtains a new global model theta_T+1 equals theta_T_G_T. This process continues until the maximum number of rounds, T, is reached. The threat model posits that a percentage, P, of the total number of clients are malicious, with the goal of reducing the global model's accuracy. These malicious clients, denoted by M and represented by the set A, share the same purpose and perform the same type of attack. They generate crafted local updates, f_g_k, from their local data distributions, which differ from those of the benign clients. These updates are designed to maximize the global optimization function f, theta, during the Florida training process. The threat model is illustrated in Figure 5. Demonstrating how malicious clients upload contaminated model updates to poison the model after receiving the global model from the server. In the realm of federated learning, poisoning attacks pose a significant threat to model integrity. These attacks can be categorized into targeted and untargeted attacks, with the former aiming to manipulate specific inputs and the latter seeking to degrade overall model performance. Examples of untargeted attacks include label flip attacks and gradient modification attacks, such as inner product manipulation. Defenses against these attacks have been developed, including client-side defenses that modify local training algorithms and rely on benign clients, as well as server-side defenses that decrease aggregation weights of malicious client updates or perform clustering and aggregation of benign clients. Server-side defenses like multi-crumb and normclipping are notable examples. Differential privacy methods also demonstrate efficacy in mitigating model poisoning attacks. However, current solutions face limitations, such as requiring representative benign data on the server, incompatibility with client selection, or maintaining reputation scores for each client on the server side. To address these issues, the CosDefense algorithm was proposed. This algorithm calculates cosine-similarity scores for each client, takes their absolute value, and performs min-max normalization to better differentiate between malicious and benign clients. The server then defines a threshold value as the mean of current scores and clusters clients accordingly, labeling clients as malicious if their score exceeds the mean value and benign otherwise. Algorithm 1, CosDefense, is a novel approach to enhancing the security of federated learning (FL) against malicious attacks. It operates by taking as input global model parameters, local updates from sampled clients, and an aggregation method. The algorithm first initializes a set of benign clients and computes the cosine similarity between the global model and local updates for each client. These cosine similarity values are then normalized, and a threshold is calculated as the mean of these values. Clients with cosine similarity values below this threshold are identified as suspicious and removed from the aggregation process. The remaining clients' updates are aggregated using the Fed-AVG method, and the global model is updated accordingly. The experimental setup is based on the use of several datasets, including dataset statistics and partitioning methods. The noneiid partitioning method follows previous works, where clients are divided into groups, each assigned a proportion of training samples. Attacking clients are distributed evenly across groups, and the noneiid degree is controlled by the probability queue. The baseline implementations and parameter selections are outlined, including the implementation details for crumb and clipping median, as well as the no defense case where the server only performs Fed-AVG aggregation. The experimental configurations are also described, including the computing server and GPU specifications. The experimental results show that CosDefense outperforms other defense strategies under the IPM attack, demonstrating its stability with changes in the noneiid degree. These findings underscore the potential of CosDefense to enhance the security and robustness of Florida systems. The CosDefense model's performance is comprehensively analyzed in comparison to other defense baselines, including no defense, crumb, and clipping median. As shown in Table 3, CosDefense outperforms all other models in terms of global model accuracy across various datasets, including MNIST, FMNIST, and CIFAR-10. These results demonstrate CosDefense's high resistance to data heterogeneity compared to other defense baselines. Figure 6 illustrates the accuracy performance on the MNIST dataset under different noneiid partition levels, visually representing the robustness of CosDefense against data heterogeneity and further supporting its efficacy as a defense mechanism. The paper concludes by discussing potential future research directions, specifically the combination of CosDefense with existing secure aggregation frameworks. However, implementing CosDefense on top of secure aggregation frameworks poses a challenge due to the encryption of local model updates, making them uninspectable by the server. This limitation highlights the need for further investigation into integrating CosDefense with secure aggregation frameworks effectively.